A very good morning, all of you. Myself, Mrs. Mansi Agarwal, Assistant Professor, Department of CSE AIML, ABES Engineering College, Ghaziabad. Today, we will be discussing our next topic of data structure, that is insertion sort. Insertion sort is a comparison-based sorting algorithm that builds a sorted array one element at a time by inserting each element into its correct position among the previously sorted elements. So in order to understand how the insertion sort works, let us take an example and try to understand the technique behind this sorting algorithm. Suppose we have an array with 6 elements. Let us just try to make this array. The elements of the array are 100, 60, 90, 30, 40, and 50. So the basic idea behind insertion sort is that at any point of time, the array will be divided into two parts. The first part is the sorted array, and the second part is the unsorted array. And our task will be to take one element from the unsorted array and place it at its appropriate position in the sorted array. So to start with, only the first element of the array will be considered as the sorted array, and the rest of the elements will be considered as unsorted arrays. The task for the first iteration is to take the element 60 and place it at its appropriate position in the sorted array. So after first iteration, after first pass, the array will change its state to this: 60, 100, 90, 30, 40, and 50. So after first iteration, two elements, that is 60 and 100, will now comprise of the sorted array. The rest of the elements will be the part of unsorted array. In the next iteration, again, we have to take one element and place it at its appropriate position in the sorted part of the array. So after this iteration, the array will look like 60, 90, 100, 30, 40, and 50. The first three elements are now sorted and the rest are the part of unsorted array. Again, for the next iteration, we will take the next element, that is 30, and we will place it at its appropriate position. We will insert it at its appropriate position in the sorted array. So the array will look like 30, 60, 90, 100, 40, and 50. First four elements are now sorted array, and the last two elements are the part of the unsorted array. Again, we will take 40 and place it, insert it at its appropriate position. So the array will become 30, 40, 60, 90, 100, and 50. At this point of time, n-1 elements are now sorted and only 50 is left as the unsorted array. Now we have to place this also at its appropriate position. And after this iteration, you can see that the array is now completely sorted with the values 30, 40, 50, 60, 90, and 100. So we can see that for 6 elements, we have to take 5 iterations, 5 passes. So if there are n elements, then we will be needing n-1 iterations. Now let us try to build the algorithm for what we have done so far. If you can see that we have, in every iteration, we have taken one element. Let us consider this element as the key element. we have taken one element like 60, then we have taken 90 as the key element, then 30 as the key element, then 40 as the key element, and last we have taken 50 as key element. So I can say that we have taken a variable key and we have placed one element, I can say A of I, into this key, where I is beginning from the second index. From the second index, it is going till the last index. So I can say that I is taking up the values from 2 to n. And what we have to do here is we have to place this element inside AI into another variable key. Now, as you can see, suppose consider the last iteration in which we have placed 50 at its appropriate position. What exactly are we doing? What exactly are we doing? Let me just make this array one more time. This is at this particular point of time, it was 30, 40, 60, 90, 100, and 50. So basically, how we are placing this 50 at its appropriate position, we have taken a variable key and we have placed this value inside this key variable. Now what we have done is we have taken another variable j and we have assigned this j as the index just prior to the key element, right? So we can say that j is equals to I minus 1. What I'm doing is I'm constantly copying this value in the next block. So this will become 100. This will become 90. Again, I have to place 60 here. So this will become 60. Till what time I have to do this? Till the time I have not got a value which is less than the key value. Till the time I have not got a value which is less than the key value, to keep on placing the values on the next block, right? So I can say that I have taken an index j, which is taking up the value, the index just prior to the key value, that is I minus 1. And then repeatedly, that means I have to put a loop. Suppose I'm taking a while loop. Till the time the value of aj is greater than key, I have to place aj to aj plus 1. I have to place aj to aj plus 1. But we have to consider one more thing here. Suppose, let us take this example in which we have taken 30 as the key value. We are not getting any value which is less than 30. But the value of j, while decrementing the value of j, it has reached to the lower bound. It has reached to the lower bound of the array. So here we have to also check that the value of j should be greater than equal to 1. Only till this time we have to place the value of aj into aj plus 1. Repeatedly, we have to decrease the value of j, that is we have to decrease the value of j, that is j is equals to j minus 1. Right. When we will come out of this while loop, we have to simply place the value of key at j plus 1th index. At j plus 1th index. This is how this insertion sort is going to work. So let us quickly see the algorithm. The algorithm says that we have taken a array, we have taken a as a parameter and n, that is the length of the array, as parameter. And then the value of I is going from 2 to n, as we have discussed in the previous slide. We have taken the value of I from 2 to 1 because the unsorted array will start from 2 and the selection of the key will start from the second index. So I will be equal to 2 to n. We have to place j as the index of the previous element. So j will take up I minus 1 and the key will be a of I. Till the time j is greater than equal to 1 and a of j is greater than key, we have to simply copy the value to the adjacent block, that is aj plus 1, aj plus 1 is equals to aj, and repeatedly we have to decrease the value of j, and at the end we have to just copy the value of key at j plus 1th index. Let us now quickly try to implement this code. So I'm just including stdio.h, that is the header file. Let us now make the user-defined function with the name insert or insertion sort. As we have already discussed, we will be taking up two parameters, that is the array and the number of elements in the array. Now, what we have to do is we have to take I, j, and key variables, wherein we have to start the loop. Now, as we are implementing, the second index will start from 1, although we discussed during the algorithm that I will start from 2, but there, as it was algorithm, we were considering the first index to be 1. Here, we will consider the first index to be 0. So, I will begin from 1 and it will go till the last element, that is n minus 1. So, I is less than n, I plus plus. Here in this loop, we have to first assign ai to key, that is key is equals to ai, and we have to put I minus 1 inside the variable j. Now again, the nested loop for comparing the value of key with the previous sorted elements, we have to use a while loop where j is greater than equal to 0 and a of j, as discussed, a of j is greater than key. Then in this situation, we have to simply copy each element in the next block. So aj plus 1 is equals to aj, and we have to continuously decrease the value of j, that is j minus minus, or j is equals to j minus 1. After coming out of this while loop, we have to finally place the key value at its appropriate position. So aj plus 1 is equals to key. Now let us quickly implement the main function. Here I'm taking an array ARR and I am placing some values inside this array. Let us suppose place the values that we have taken. That was 100, 60, and then we had 90, then we had 30, 40, and 50. So these were the values. Now let us try to find out the number of elements. We can simply write here size of. We can simply use the size of operator, size of ARR, and I can divide it with the size of int to get the total number of elements in the array. Now simply call the insertion sort user-defined function with ARR and n. As we will come out of this user-defined function, we can simply display the sorted array. The sorted array is, and for this we need another loop. So we can take int I is equals to 0 to less than n I plus plus, and we can write printf to display each element %d with some space and ARR. As we are in main function, we have taken ARR as the name of the array. So I think this should work. Let us just run this code. And yes, the array that we have taken is sorted with the help of insertion sort. Let us now discuss the complexity of insertion sort. And in order to do so, let us consider an array in descending order. Let us just take the similar elements, but in descending order. So suppose we have 100, 90, 60, 50, 40, and 30. So you can see that in order to store the first key element at its appropriate position, we have to compare this 90 with one element, that is 100. So in the first iteration, the number of comparisons will be 1. But in the second iteration, we have to compare this 60 with both these elements, because both of them are greater than this key value. So for the second iteration, the number of comparisons will be 2. Similarly, for the third iteration, the number of comparisons will be the number of elements prior to this key value, that is 3, and so on. So for the last element, the number of comparisons required will be n minus 1. Here we are discussing the worst case where the array which we have got as input is stored just opposite, that is in the descending order, and we want to sort it in ascending order. So here we know that 1 plus 2 plus 3 up to n minus 1 can be represented as n minus 1 into n by 2, which is equal to n squared by 2 minus n by 2. And we know that as this is a function of n with the highest order n square, so this can be represented as big O of n squared. So this is the worst case complexity of insertion sort. And if we want to discuss the best case complexity of insertion sort, so suppose we have the similar elements, but they are stored in ascending order and they're already sorted. So suppose this is 30, this is 40, this is 50, then we have 60, then we have 90, and then we have 100. So you can see that when we will start selecting the key value from the second element and we will compare it with the previous element, there will be only one comparison. When we will select the next key, that is 50, it will only be required to compare it with the previous element, one previous element only, because this 40 is less than 50 and the while loop will break and will come out of it. So there will be only one comparison. In similar way, for all the n minus 1 key values, we will only have to do one comparison. So therefore, the total number of comparisons here will be n minus 1. Again, this is a function of n, but the highest order of n is n raised to the power 1. So this can be represented as omega of n, as we are here discussing the best case complexity of insertion sort. So the time complexities can here be briefed as the average case as O(n) square, best case as omega n, and worst case as O(n) square. When considering the space complexity, as you can see that we have not taken any other data structure that is dependent upon the length of the input n. So the complexity will be constant and it can be represented as O1. Thank you.